Hey everybody, Mr. Bells here. This is going to be a video on exponentials for Precalc A section 3-1. Exponentials move in with a little introduction to logistics, making sure that we're comfortable with how these things play out. So we're going to start off with this discussion here. You know that basic exponential equations, this thing is not basic exponential equations, what defines them is the variable is actually in the exponent spot. So if we don't know what that is, or that has change, it just means that this number right in here, whatever the 1 plus or minus r is, gets multiplied over and over and over and over and over again, t amount of times. And if 1 is greater, or if this number right here is greater than 1 plus interest rate or rate, then it's going to grow. And if it's less, again, whatever's in the parentheses is less than 1, or between 0 and 1, then it's going to shrink over time. Okay? So let's just say that I had this one problem. Maybe I've got a $35,000 truck, and it's depreciating at 12% every year, and I want to know what the value is in 8 years. Well, that means that we can use this nice little formula right here. The ending amount, A, equals the starting amount, P, which in this case is 35,000. So I write A equals 35,000, parentheses 1. Now you have to decide, does truck depreciation mean that it goes up or it goes down? And some of these things you just have to know, but depreciation means that it's going to lose value over time. So it's going to be minus 12%. To change a percent to a decimal always has to be 2 places to the left, so that's minus 0.12 raised to the t, and that t is going to be, in this case, 8. So because of the fact that I just have it like this, I can answer that question on my home screen here. Clear, so I can do 35,000 parentheses 1 minus 0.12 close parentheses raised to the 8, and I get $12,587.20. And the other thing that I could have asked on this one is, like, maybe I want to know, when is it going to be worth, I want to resell it, when's it going to be worth $5,000? Okay, well, that, if I'm asking that question, then I want to know what this A is. Okay, I want to know, how much time it's going to take until this truck is worth 5,000. So 5,000 is the value of A. Well, I could try and do that algebraically, and we talked about it back in data class, that we use something called logarithms, and we'll get into those in more detail in just a few more days of this class. But for right now, I'm going to go ahead and do it by way of a graph. So 35,000 parentheses 0.88. I can change that. If I know that 1 minus 0.12 is 0.88, that works out for me. So you can see that it's decaying, it's depreciating because it numbers between 0 and 1. Raised to the t, because now I don't know what it is. And again, we have to use x in our calculators, y equals format. Go ahead and put in 5,000 here and zoom 6. Of course, if I zoom 6 it, and this is where a lot of students are still, even through this course, are having issues with windows. Like, what the heck's going on? Well, my window represents the x and the y spread for the variable. So right now it's going from -10 to 10. And I get a lot of students that'll do this. They'll go 0 to 40,000 in this case, because the truck's value is 35,000. But what we have to keep in mind is that this x in this case is the number of years. And thinking about going up 40,000 years makes no sense whatsoever. In fact, we already knew the answer at 8 years took us down to 12,000. So I'm feeling I don't want to go much more than 20 years. Now, y, that's a dollar amount. I'm totally okay to go 40,000 here. Now, I know I only need to know it at 5,000, so I could have put it in at like 6 or 7,000. But I like to see it where it starts up there too. Okay. I go ahead and hit graph, and there is the value of my truck over time going down. That is the constant of 5,000. Second trace, number 5, enter, enter, enter. And I can see that it takes me 15.2 years to be able to answer that. So hopefully that was a quick little review on being able to use your calculator to answer basic exponential equations, whether or not it's going up or down. So reminder again then, on problem number 2, that this right here tells you if it's growing or decaying to an extent, I'm going to say. Okay. So what this problem is showing here is that the y-intercept, or the starting point, both the same. If I was to graph this, and that's 50, that's 100, that's 150, 142 is right there. That's where it's going to start at. This number 1.86 means that it's going to grow because it's greater than 1. So the graph's going to look something like this over time, and this is going to keep going down. It's some amount. It will never cross, right? It will never cross the x-axis. That's called a horizontal asymptote. But it's going to come down in that some way, shape, or form. Again, the bigger the number this is, the steeper it would be as it goes over there. Okay, now here, we're looking at this and we're like, hey, that number is between 0 and 1, so that means that it should shrink, right? Right? Wrong. We have to remember that a negative exponent changes things. It basically flips that fraction. So I could rewrite this as 5,000 equals 426 to the 47 hundredths. I'm hoping everybody agrees with that, because 0.47 is 47 hundredths. Now, because that exponent was negative, it's really the same thing as writing the reciprocal of that fraction to a positive x. So again, negative exponent of 47 hundredths equals a positive exponent of 147ths. And now you can look at this number, and this number is definitely greater than 1. In fact, it's greater than 2, so it's more than doubling each time. So in that case, this actually is an exponential growth function. So we want to look at this, but we need to look at it in tandem with what the heck the exponent is actually, whether it's positive or negative. Okay, so this is what I want you to do. I want you to guess. I want you to guess, what do you think x is in this particular problem? So I'm hoping this makes sense, that if I converted, and this is a little bit more than doubling. So if I double it once, it goes to 850. Double it twice, it goes to 1,700. I double it 3 times, it goes to about 3,400. And if I double it 4 times, now it's greater than 5,000. Okay, so I'm thinking, as I'm logically processing through this stuff, that maybe this solution is somewhere around 3.5. Okay, one more time, do you process that out? Weird to think of it this way, right? Okay, I need this to be negative because I can't get 426 to become 5,000, correct? If it's supposed to be shrinking, so my x has to be a negative number, or it will end up being a positive number with a negative out front. So I have to go backwards in time to be able to get this. Is that okay? Now, I converted it. I thought about it. I'm like, that's about 2 for doubling. I get 3.5. Let's check it on the calculators. You guys do it on your own first. Pause the video. Try it. Go. And hopefully you turn the video back on now after you've actually checked it. So let's go. Here we go. I got 5,000 parentheses 426 close parentheses. Oops, sorry. 5,000. Thought I hit the up arrow already. 426 parentheses 0.47 parentheses raised to the negative x. Again, remember, I thought my answer was going to be somewhere around 4. So I'm going to go x max 5. I feel pretty confident with the 4 thing, specifically about 3.5. And here I need it to be 5,000, so I'm going to go 8,000. I hit graph. There's where it is, and going across. And second trace, number 5, enter, enter, enter. And you can see I got 3.26. Pretty good guess for 3.5 to 3.26. Okay? So again, just talking a little bit more about exponentials. Well, the next thing is going to be an exponential data set. So I've got data right here, and I believe that this stuff models an exponential, so we're going to practice on our calculator again. Hopefully you're getting pretty good at these. We're going to go stat and edit. Here we go. And I'm going to get rid of all of this data. So I can do that by hitting second, plus sign, number 4, clear all this, hit enter, stat, and edit. So I'm going to put the x's into L1, so 1, enter, 2, enter, 5, enter, 7, enter. I cannot put the 15 in because I don't have a corresponding y value. I'm going to use the first 4 data points to find an equation, and then I can use 15 to find out what it's going to get me. Okay. Over here, I got 300, I got 375, and I got 732, and I got 1144, and I got those. So let's do a stat plot first. So I'm going to turn my plot on. I'm going to do a scatter plot with L1 and L2. Does that look okay? I just kind of want you to see the curve. You don't have to do this to get an equation. Just want you to kind of understand what the data points look like if I was to plot them. Go to my window. My x's went from 0 to 7, or 1 to 7, so I'm going to go 0 to 8. My y's went from 300 to 1144, so I'm going to go to 1500 from 0. That's totally good. I mean, I could put this at like negative 300 if I wanted to, just to be able to see the stuff. Go to my y equals and get rid of anything old that's in there. And then hit graph one more time. That's my window. That was my stats. And hit graph. So I can see that there's definitely, it's not a straight line, right? And I'm just going to go through a few of these ones just so you can see them. So stat and calc, and let's assume that it was linear. Maybe it's linear. I don't know. I get a R value of 0.986. I'm like, ooh, that's pretty good. That actually is really good. But again, I only have 4 points, so some of these things are going to be better just because of it. Stat, calc, let's do a parabola. And my parabola is 0.9997. That is flipping really good. Now, I don't want to do a cubic because I know that 4 points will always give me a perfect cubic because that's what I need to get a cubic equation. So I don't want to assume that it's cubic unless there was some reason. Maybe I was dealing with volumes of 3-dimensional shapes for something that I needed to cube root in there that a cubic would work for me. So let's do one more. Stat, calc, and I'm going to do exponential regression because again, there was a little curve to it. Whoa, 0.99999996. I'm feeling pretty comfortable that that's what it is. I can look really close at this. That means my starting value is about 240 at point times 0. And my growth rate is about 25% because it's 1 plus whatever that amount is, 0.249, so 1.249. So I'm going to do this again, stat, calc, exponential regression. I might as well go ahead and copy that in. So I go down here to store the equation. I hit vars, and I hit y vars. I hit function, I hit y1, and I hit enter, calculate, poof. This is the exact same equation again, except now you can see that it copied that thing right into there so that I don't have to worry about retyping it. I hit graph, and dead on, that is a winner. So now, still trying to find out what this 15 was. Since I have the equation, I'm going to go ahead and just do table setup. I'm going to start it at 15, just like that. Again, second window says select your table, second graph. Gives me that value, and I get 6,813.3. I'll go ahead and put that in. 6,813.3. Awesome. Now, again, one of the things that this thing said is that I should start about 240, right? About 240. And it also says that it looks like the growth rate's about 1.25. If I round that up a little bit, about 1.25. So let's do some quick approximations from my home screen just to make sure that you understand how these exponential functions are working. So I got a little glare in the room right now on that one. So if I start, and I know that my factor is 1.25, and I do 300, if I was to go backwards, I'd actually be dividing by 1.25. So watch, division by 1.25, and I hit enter, and you can see I got 240. That's exactly what the starting point should be. Now let's go a little bit different on this. Let's go the other direction. 300 times 1.25, and I hit enter, and you can see it's 375, and that's exactly what that number is. And if I times by 1.25 again, I hit enter, I get 468, and that's not that one. But then that makes sense for everybody, right? We're missing the third and the fourth. So I actually have to enter, multiply by 1.25 again, and then again, and now you can see that 732.42 is really close to 732, and again, that was the fifth one. So 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, and 15th, you can see how the approximation is really close. That's all exponential functions are, is repeated multiplication. Okay. So, how do I get an equation just if I have a graph? Well, let's try and remember again exactly what the equation looks like. The equation is always y equals a times b something to an x power. A is the starting point. So if I look over here at this graph and I see that it starts at 14, I know my equation is y equals 14, parentheses, right? And raised to the x, however many times that is. So what I need to know now is what would this thing be right here in order to be able to get it so that if I multiplied it from 0 to 1 time, 2 times, 3 times, I would actually get a value of 72. Does that make sense? So how can I do that? Well, I can go stat, calc, or stat, edit, and then put those points in. So second plus number 4, clear all lists, poof, stat, edit. And I'm like, hey, does an exponential function work with only 2 points? Could we do a 2-point summary of this? I'm thinking we probably could. So 0, enter, and 14, enter, and 3, enter, and 72, enter. You like that? Like, whoa, yeah, that's good. Stat, calc, exponential regression. And you can see that it says the growth rate is 1.726. So I'm going to go ahead and put that in right now, 1.726. And I'm going to check and see if that actually works. So here we go. So I have 14, and I multiply by 1.726. I hit enter. That's the first multiplication by it, right? Times 1.726. That's the second multiplication by it. And the third multiplication should get me to 72. And look at that, I'm at 71.986. Sweet. So the calculator was able to do the exponential regression for it. Can we still do it in our heads? Is there a way for that to work? Remember, the number is 1.726. And I know that I need repeated multiplication, right? So I'm going to try this. Let's see it. 72 divided by 14, enter. I got 5.14. So I did the division between those to see what is going on. And now I also have 3 and 0. Well, I can't divide by 0. That doesn't do me any good. And if I divide by 3, did that get me there? Yeah. Well, that's pretty darn close on that, isn't that? Awesome. Now what if I did 72 minus 14, enter. And I looked at that and divided by 3. That doesn't really get me there at all, does it? Okay, so what are we looking for? We're looking for the division of those divided by how many times it goes up. Okay? So, go ahead right now, take a second, and see if you can find out what that value is using that equation. Pause the video right now, actually do it, put it into your calculator. Okay, so one of the things I would ask you to do is see if it worked for another one. Now, you guys know a second ago I had my calculator out here, and I did the 72 divided by 14, and then I took that answer and I divided by 3. And we got 1.71, which is really close to this. But since there's only 2 points, it really should be perfect, shouldn't it? I would think it should be perfect. So maybe I'm not actually dividing by 3, because that would assume there were 3 linear steps that were going up to get to it. I think really what I want to do, so I want to take that number, whatever the ratio is between these two things, and take the cube root of it, the 3-step jump, because that's what repeated multiplication is. Now watch on the calculator, it's kind of magic right now, watch. 72 divided by 14 that we did before, right? Remember, division by 3 got me that, but that isn't really 1.726, and we don't have enough data points to have had a rounding error. Let's try the same thing again, this one right here, watch. And now watch how it happens when I take the cube root of it. So second, and math, or just math, my cube root, I didn't do that answer. So math for cube root, I'll pull that answer down here, and poof, look at that, 1.726. 1.726. That's actually dead on. So when I ask you to try different things, sometimes you're going to be like, whoa, that looked like it worked, but it really didn't work. And when I did this, okay? So how do I find out this anytime? I take y2 divided by y1, yes? And I take the nth root based on x2 minus x1. Okay, so let's try right up here. Let's see if this works out on this one. Remember what the rate was on this just a little while ago? So I'm going to try it. So I got 1144 divided by 732, enter, right? I got that number. Now, how much of a jump is it with the x's? It's a jump of 2, so I need a square root. So I'm going to do second square root, second answer, hit enter, and there's that same 1.25 that we got last time. Okay? So, hopefully we learned some stuff there about how to get your growth rate or your decay rate based on 2 values that you know exist. The ratio of the y's to the nth root of the difference of the x's. Okay, so now we're going to talk about transformation. So you guys know that, say, this is a basic exponential growth function. It has a horizontal asymptote at 0. So what happens when we take one of these things and we put a negative in front of the x? Well, let's take a quick look. So I go here, I'm going to turn that stat plot off. And I'm just going to do 4 raised to the x. I hit graph. We should zoom 6 this, zoom 6 it. Looks just like that, right? That's what an exponential growth function looks like. So what happens when I put a negative. So let me insert a negative on that thing, and I hit graph, and you can now see that it becomes a decay. And I'm hoping that makes sense, right? Because 4 to the negative x is the same thing as 1/4 to the positive x. Cool. Now, what happens if I put something out here like this? Plus 8. Well, that should, like everything else, take that entire thing and shift it up 8 units. Good deal. So if a number plus out here moves it up, would a number minus out here move it down? Look at that, and it does. So now the question is, how do I move it left and right? So I'm going to do a little shift right up here by the x. So let's do like a +7 and hit graph. And now you can see that that moved it all the way over here to the right. And you're looking at like, wait, what? That isn't it supposed to always go the opposite of that? Well, it would, except for the fact that you've got that negative on your x. So, okay, follow me here on this. If I had y equals 2 to the x plus 6, this should take a graph of 2 to the x and move it 6 to the left. Okay? But if I have this 2 to the negative x plus 6, what we really have to think about is when that reflection occurs. So I'm going to factor this negative out. So this is equal to 2 to the negative, right, that's the reflection, of x minus 6. And that's why when I just did this, it technically is like a -7 up there, and that's why it moved it to the right. Okay? Now again, it's not going to touch at 7. It's not going to touch at 7 right here. And the reason is because I got this whole -8, and that's moved it. That's moved it. Okay, so let's start again. So 2 raised to the x graph. That looks like that. 2 raised to the negative x. That looks like that. 2 raised to the x plus 7, where the +7 is in the exponent spot. You can see that moves it 7 to the left. Y equals 2 raised to the x, and I come down here at -4. That moves it down 4. So I'm hoping you can follow these transformations. Okay. Okay, we're getting closer. We're getting closer. Okay, so exponent properties. These are just some reminders again, and some of them I've already talked about in this video, but I put the notes up here before. So you know that 3/4 to the x is the same thing as 4/3 to the negative x. So 4/3 to the negative x is the same thing as 3/4 to the x. The negative exponent simply can be changed to positive by flipping your fraction. This over here, I don't know if you know this because this is a little bit weirder for you, but 6 to the 2x plus 8 is the same thing as 6 to the 2 times x plus 4, where the only thing that I've done here is factor out a 2. Okay? Factor out a 2. However, if this 2 is on the outside, and this is multiplication right here, just like this, I can go ahead and do the power to that. So 6 squared, which is 36, and then raise that to the x plus 4. So I can do it to each individual ones. Good deal? Right down here, this is not true. 3 times 2 to the x does not equal 6 to the x. I cannot multiply these two numbers together, even though I have kids do it year in and year out. That is an exponent, and PEMDA's E is right there. 3 times 2 is multiplication, that M is right there. I cannot do multiplication before I do exponents. Okay, so does not work. Do not do that. What else is true? If I have 4 to the x times 4 to the third, that is equal to 4 to the x plus 3. I can simply take those two things if they're the same bases, and I'll add those exponents together. Just to make sure, though, x and 3 added together is x plus 3. It's not 3x. That's a completely different situation. Also, what's true over here, 4 to the x squared is the same thing as 4 to the 2x. Remember, old calculator people, make sure that you put those in parentheses. Final thing that we're going to talk about right now is we're going to talk about a logistic equation. So, generally speaking, a logistic equation is an exponential equation that tapers off, that can't continue its exponential growth rate because there's a limit to its growth. It actually has two horizontal asymptotes, one where the graph, if it's like this, would go to the left, one up here where the graph would go to the right. So two distinct horizontal asymptotes. I can find out what these horizontal asymptotes are, what the inflection point might be, all of these different things based on the equation, and we'll get into that in a lot more detail later. But let's at least see if we can graph it so that we can see that this thing does look like one of these things. So go to your calculator, turn it on, clear all of these things out, and there we go, y equals. So I got 18 divided by, and because this is all in the denominator, I need a big set of parentheses, 2 plus 3, parentheses 0.6, close parentheses, raised to the x. And again, it's just the 0.6 to the x, just the 0.6 to the x, not the 3 times that to the x. I cannot make this 1.8, right? That was kind of my rule just a few minutes ago. Don't do that, don't do that. And then close parentheses and graph. Look at that. It looks just like what we said it would. Is that good? Now, question. What are my two horizontal asymptotes? Well, if I hit trace and I go here to the right, and I'm like, it's at 6, the y value right here, it's at 7.9, it's at 8, it's at 8.7, 8.8, 8.9, 8.95, 8.97, 8.98, 8.99, 8.999. I don't think it ever gets past 9. Like, where does that 9 come from? Clear that out. Zoom 6 again. Why does it max out at 9? Well, if you look right over here, when you're going to the right, x is heading towards infinity, correct? X is heading towards infinity. Awesome. So that's a giant value in there for that x. Well, what happens when we multiply 0.6 over and 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 over again an infinite number of times? You can see here, clear, right? Clear. 0.6 twice is 0.36, 0.6 cubed is 0.216. You can see that it's getting smaller, right? Over and over and over again, getting smaller and smaller and smaller and smaller and smaller. You're in scientific notation now. Whoa! So if that's approaching 0, 3 times 0 is 0. So I have 18 divided by 2, and that's where that 9 comes from, right? So we can kind of just cover that up and go, oh, look, that's where my top horizontal asymptote is. Now, I'm going to go back to my graph. Why does it flatline here at 0? Why can it not get, why can't it get smaller than that? Well, this is an exponential decay function, correct? So if I was to graph that, and it looks like this, can that graph ever become 0? Or it can't become 0, and it can't be negative. No negatives. And if it can't be negative, then this fraction always has to be positive. Does that make sense? And if I have a positive divided by a positive, that means it always has to be above that axis. Now, why could it get really, 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 really small? Well, if I took this and went backwards in time, right? Went backwards in time, that's this value. Like if I put negative 10 in for x, that's really like multiplying by 0.6 over and over, or dividing by 0.6 over and over and over and over again, which means this fraction is going to get really, really big, and 18 divided by a ginormous number is close to 0. That's why when it goes to the left, it gets closer and closer to 0. So I'm hoping that's okay on a lot of this stuff. Continue to watch these videos. I'm hoping that they're helpful. Take your time on the homework. Remember that they have homework helpers on there too. And make sure you're doing your own work, or at least every time you do a problem that you know how to do it. We'll talk to you later. You guys have a great day.